Welcome everyone. Today we'll explore degradation threats to the gas process systems. Understanding internal and external corrosion mechanisms, identifying and managing corrosion risks. This presentation will cover key process stages, internal and external threats, relevant inspection method to detect and mitigation strategies. Introduction: Why degradation matters. Gas process systems are exposed to various chemical, physical threats and operate under harsh conditions. Degradation can lead to failures, safety risks, reliability, and efficiency, and costly downtime. Understanding threats helps in planning effective inspection and mitigation. We'll explore the types of degradation threats across different stages of the gas process system, focusing on internal and external mechanisms. Degradation is not just a technical issue, it's a business and safety concern. Understanding the threats helps us protect assets and ensure operational continuity. Overview of the gas process system. Key stages in the gas process: separation, removes liquids and solids from gas; compression, increases pressure, may involve 1 to 3 stages; glycol contactor, dehydrates gas using glycol; fuel gas conditioning, prepares gas for combustion; metering, measures flow and composition; glycol regeneration, recycles glycol for reuse. Each stage has unique operating conditions: temperature, pressure, and chemical exposure that influence the type and severity of degradation threats. Internal threats in wet gas areas. Internal corrosion risks in wet gas zones. Number 1 is CO2 corrosion threat, forms carbonic acid in presence of water. Relevant NDT methods to detect CO2 corrosion: ultrasonic thickness test or UT, radiography, corrosion probes or corrosion coupons, and intelligent pigging. Number 2 is H2S corrosion threat, leads to sulfide stress cracking and hydrogen-induced cracking. Relevant NDT methods to detect H2S corrosion: ultrasonic thickness test or UT. Radiography, dye penetrant and eddy current. Number 3 is oxygen or O2 corrosion threat, leads to accelerates oxidation and pitting. Relevant NDT methods to detect oxygen or O2 corrosion: ultrasonic thickness test or UT. Radiography, corrosion probes or corrosion coupons. Number 4 is MIC or microbially influenced corrosion threat, caused by bacteria, especially in stagnant zones. Relevant NDT methods to detect MIC or microbially influenced corrosion: ultrasonic thickness test or UT, radiography, microbial sampling, and biostuds or sidestream monitoring. Number 5 is galvanic corrosion threat, occurs between dissimilar metals. Relevant NDT methods to detect galvanic corrosion: ultrasonic thickness test or UT, radiography, and visual inspection. Number 6 is crevice corrosion threat, localized attack in gaps and joints. Relevant NDT methods to detect crevice corrosion: visual inspection during maintenance. Ultrasonic thickness test or UT, might limited and dye penetrant for cracks. Number 7 is erosion corrosion threat, high velocity flow damages surfaces. Relevant NDT methods to detect erosion corrosion: ultrasonic thickness test or UT, radiography, acoustic probes, intrusive erosion probes. And number 8 is acid attack threat, from organic or inorganic acids in process fluids. Relevant NDT methods to detect acid attack: ultrasonic thickness test or UT, radiography, and corrosion probes or corrosion coupons. Wet gas environments are highly corrosive due to the presence of water and aggressive gases. These threats are most prevalent before dehydration. Wet gas areas are the most vulnerable. These threats often act synergistically, accelerating damage. Internal threats in dry gas areas. Stability in dry gas zones. Dry gas significantly reduces corrosion risk. No water means no electrolyte for corrosion reactions. Monitoring still required for unexpected moisture ingress. Once gas is dehydrated, the risk of internal corrosion drops significantly, making these areas more stable. Dry gas systems are relatively safe, but vigilance is key, especially after maintenance or process upsets. Glycol regeneration threats. Corrosion in glycol regeneration unit. Number 1 is CO2 corrosion threat. Concentrated CO2 can lower pH, leading to general and localized corrosion. Relevant NDT methods to detect CO2 corrosion: ultrasonic thickness test or UT, radiography, corrosion probes or corrosion coupons, and intelligent pigging. Number 2 is acid attack threat. Thermal degradation of glycol forms organic acids, increasing corrosion risk. Relevant NDT methods to detect acid attack. Ultrasonic thickness test or UT, radiography and corrosion probes or corrosion coupons. Number 3 is localized corrosion threat, risk in reboilers and piping due to acid concentration and heat. Relevant NDT methods to detect localized corrosion, ultrasonic thickness test or UT for wall thinning, radiography for internal damage and visual test during shutdowns. The regeneration process can concentrate corrosive agents, especially CO2 and acidic compounds, leading to localized corrosion. Glycol systems are often overlooked, but they can be hotspots for corrosion due to chemical concentration and heat. External threats, external corrosion and CUI. Number 1 is external corrosion threat. Atmospheric, marine, and soil exposure often affects coatings and fasteners. Relevant NDT methods to detect external corrosion, visual inspection, subsea video inspection using remote operating vehicle or ROV, and CP potential monitoring or survey. Number 2 is CUI or corrosion under insulation threat, hidden damage under insulation, especially on warm/hot pipework. Relevant NDT methods to detect CUI or corrosion under insulation, visual inspection, strip and search, real-time radiography, thermography and pulsed eddy current. Number 3 is FF or fire flood threat. Environmental events accelerate degradation, especially in exposed areas. Relevant NDT methods to detect FF or fire flood, visual inspection, ultrasonic thickness test or UT for post-event assessment, radiography for structural integrity. External threats are often underestimated, harder to detect and often more severe. CUI is particularly dangerous because it's hidden and can lead to sudden failures. Mitigation strategies to managing degradation risks. Number 1, material selection, use corrosion-resistant alloys. Number 2, protective coatings, barrier against corrosive agents. Number 3, corrosion inhibitors, chemical protection in wet systems. Number 4, inspection programs, routine checks using NDT methods. Number 5, insulation maintenance, prevent CUI with proper sealing. And number 6, cathodic protection, electrical protection for buried assets. Mitigation is multi-layered. Design, operation, and maintenance all play a role. A proactive integrity management plan is essential to mitigate these threats and extend asset life. Conclusion, key takeaways, degradation threats vary by process stage and environment. Wet gas and glycol systems are high-risk zones. External threats like CUI require special attention. Proactive inspection and mitigation ensure system integrity. Understanding where and how degradation occurs allows us to better protect our systems and ensure safe, efficient operations. Thank you.